so we've loaded in all of the data for the roller coasters. And now we're going to start working on the roller coaster data to make some summary statistics, and this is going to be the 5-number summary. These are the most important 5 numbers in our data set as far as the box plot goes. In fact, they're the numbers as far as the box plot goes. So we're going to go to Calc after we hit Stat, 1-bar stats, tell us your data is in list 1, hit your enter key, and just by way of noticing, we see that the X bar, which is the mean of that set of roller coasters, let's see, Cedar Point Amusement Park, this is the speed of the roller coasters in the park as of 2014. So this is actually a population of roller coasters. It's not a sample, it's actually a population of roller coasters. So if we were going to report that mean, we would call that mu equals 57.5. And then the standard deviation would be sigma equals 25.24. And again, that's because we have all the roller coasters in the park. So we would use the population symbol for the mean, not the X bar. And we would use the population standard deviation symbol. And even though we're not asked to do that, I'm going to make a note of what those are at the top of the page. Let's see, let's try it out here. So mu is equal to 57.5. And sigma is equal to 25.24. And then we'll see how this stacks up with some of the other information that we're going to find here. So the arrow next to the side, next to n equals 17 for the 17 roller coasters in the population, says there's some more information down there. So we scroll down and we see that the minimum value is 6. And that's the Wilderness Run roller coaster. So it's not very fast. And then the first quartile is 40. And there are, I believe, 3 that are 40 miles an hour. The Blue Streak, the Cedar Creek Mine Ride, and the Iron Dragon all go 40 miles per hour. Then the median is 60. So the Gemini goes 60 miles per hour, and the Mantis goes 60 miles per hour. So those are the ones that are typical as far as being the median is concerned. And then the third quartile is 71. And 71 actually isn't any of the roller coasters themselves. We've got the Wicked Twister is at 72, and the Magnum XL 200 is at 72, but the Maverick is at 70. So apparently we don't have an exact third quartile, so it's going to go between those two values of 69. No, wait, let's see, 70 and 72 to get to 71. And then the maximum is 120. And that 120 is represented by the Top Thrill Dragster. So that's a pretty fast roller coaster. And then what we want to do at this point is we want to make a box and whisker plot. Now we're going to use the calculator to make it, and then I'm going to try to sketch it on the paper. So we're going to go to second and y equals and choose plot 1 and turn it on. And then we're going to go down arrow to the type, and we don't want that first type or second type, and that actually would be a histogram, so we're not going to do that one right yet. We might do one in a minute. And we have 2 types of box plots. We have this type, which is your standard box plot, And then we have this one, which shows the outliers, if there are any. So for this box plot, we're going to go ahead and choose the one that would show us the outliers, just so that we can make sure that we see if there are any, because that's going to figure into whether or not what our upper and lower fences show us. So we're going to choose that first box plot by selecting on, and then the data is in list 1. The frequency is 1. If they weren't that way, then you hit second and number 1 to get your list 1. And then 1 for your frequency, you actually have to turn off. There's a little A in that flashing cursor. I don't know if you can see that it's an A or not. But you have to actually turn off the alpha to get it to go back into numerical mode. So if you didn't have the one that's got an A in the cursor, then what you need to do is hit alpha to turn the A off. And then the mark we're going to use for the outliers is going to be those little boxes. So we're going to hit enter on that, and then we're going to press the zoom key and scroll down to number 9, zoom stat. And we see that we do have an outlier. We actually do have one outlier. So when we draw the box and whisker plot, you want to be careful to keep it to scale as much as you can. So in order for me to do that up here, I'm going to put a sheet of paper under here that has some lines on it that I can use to help me out a little bit. You may not be able to see these, but I will. So since I know my minimum is 6 and I need to go up to 120, I've got to figure out a scale that will let me see all of that on this sheet. So I'm going to start here at 0. And let's see, 10, 20, 30, 40, 50, 60, 70. Yeah, I can do 10 for each one of these. So there's my scale. Let me zoom out a little bit more so you can see it better. And it's important that you do draw these on an evenly spaced number line, because those distances on that box and those long whiskers on the sides, those are relevant. So my minimum value is 6, which would be about here. And then my medium, or excuse me, my first quartile is 40.
I don't recall us talking about quartiles last time. What are quartiles?
Quartiles are...
How do you figure them? Is bottom 25%, bottom
Yes.
15%? But how do you figure that?
The calculator actually counts up the data values and figures out how many data values are in the bottom 25% and tells you where that cutoff is.
Okay, so if you
Okay.
use a relative frequency distribution.
We're not using a relative frequency distribution.
No, but
well, yeah, you could. Thinking about what you're saying, yes, you could.
And how many values are in
The bottom 25%. Yeah. I'll go through in a minute and show you an actual way. This is not that big a data set that we couldn't do this. I'll show you a way that you can actually break it up to where you can see what's actually happening. So our first quartile is 40, the median is 60, our third quartile is 71, and 50% of the data then is between 40 and 71 miles per hour. And then 25% of the data is between 6 and 40 miles per hour. And then on the upper end, since we know the 120 is an outlier, it's way up here. It's the maximum, but it's also an outlier. We need to figure out what this volume is at the end of the whisker that doesn't quite go to the outlier. So we're going to hit trace, and you can trace on the box plot and actually see what each one of those values are. So the value that was next below 120 was 93. So it's actually going to be the end of the whisker. Now, in order to visualize why that works the way that it does, let me, it's not there. Let me open this back up. Go back to the folder that had the actual notes in it. And this is only because I don't want to have to deal with having to retype the data values. Oh, and I forgot this is not the Word document. This may not work. Well, I'll just have to go into Excel and do it by hand. I can do this with calculator, but I think it might. Well, let's just do it with calculator since it's already in calculator.
We don't have the previous 2 pages done.
Okay, I'll move back and do those. I wanted to be sure we get to these today, though, but we will move back to the other 2 pages.
Okay, because I didn't know how you get in there, QR and everything else. I guess it was on the 3rd page.
I'm going to look for the other pages. Let's see. Let's see. Okay, what I'm doing is the example, and then I'll come back and talk to you about these. Okay? Since we've got the data in the calculator, let's go back to stat and edit. And it would be easier to see what these numbers were if I had them listed in numerical order. Does anybody remember how you put the data in list 1 into numerical order? We hit stat and go down and choose either sort ascending or sort descending. I'm going to do ascending. And I want to sort the data that's in list 1. So I hit 2nd and 1 and close the parentheses. And then I hit enter. Okay? Now, I didn't see it do anything, but if I go back and look at the data, my data in list 1 is now in numerical order. And this is going to be a handy thing to be able to do, because what I'm going to do is I'm going to actually show you what the calculator did very, very quickly, in the blink of an eye, as a matter of fact, and what it takes us a little longer to do. First, I'm going to scroll through here and say, okay, how many data values do I have? Well, I have 17. Calculator tells me the 17th entry is 120. So I'm going to start out by finding, let's see, half of 17 is what?
8.5.
8.5. So I need 8 numbers in the bottom half and 8 numbers in the top half, and then that one number in the dead middle, because I've got an odd number of data values, I have one actually sitting in the middle, is the median. So let's show by hand what all of this does. We're going to start out with the 6. Let's see, let's go this way. We'll start out with the 6, and then 25, and then 40, and then we have 2 more 40s. And then we have 43 and 48. So that's 1, 2, 3, 4, 5, 6, 7. I only have one more in my lower half. And that's going to be 57. And the next number that comes up is going to be the median. And that's 60. And I'm going to move it down here because it really doesn't belong to the lower half or the upper half. It's going to sit there kind of by itself. So this is my median. Then I'm going to go list the other set of data values, and I'm going to start going backwards now. Some more 60s, a 65, and then 67, 70, 72, 72, 93, and 120. So there's the whole data set. This is my minimum value. And this is my maximum value. My first quartile is the center of the lower half. So between 6 and 57, but not looking at the values themselves, I'm just going to count into the middle. So the middle here, the first quartile, is 40 because both of those are 40. And if I counted my median as part of the lower half, then it would actually be this 40 that is the middle of the lower 50% of the data. You're only looking at position. Quartiles and percentiles are a measure of position, not a measure of value. Okay? And then the same thing, since this is the upper half of the data, you can go straight across from Q1 and find Q3. And that's why Q3 is equal to 71 because it's halfway between 72 and 70. Now, if you include the 60, then the third quartile would have been 70. And there's 2 different ways to calculate a 5-number summary, and that's including the median value or not including the median value. And it gives you a slightly different answer, as you can see here. But the way that you should do it is eliminate the middle value if there is, in fact, a middle value. Don't count it because it really doesn't, it can't belong to the upper half and the lower half, both. So you really just don't count it as being part of the data. And you say that this is the lower half and this is the upper half. So 50% of my data goes from 60 to 120, And 50% of my data goes from 57, or from 6 to 57. 25% of my data, 1, 2, 3, 4 data values out of the 17, is between 6 and 40. 4 out of 17 is 0.235, which is as close as I can get to the 25th percentile. Yes?
What is the value of this particular way of arranging the data? What does it tell you? What do you get out of it?
You can make a lot of quick assumptions about how much of the data falls between two values without having to do a lot of arithmetic. It's really just being able to rank order them and count. So the kind of things that I would get out of this would be 25% of the data is between 6 and 40. And I could also say 25% of the data is between 60 and 120. But a more important thing to say, and this is since we talk a lot about measures of center, is that 50% of the data is between 40 and 70 or 71. You can find the range of the data automatically from this. You have a good measure of typical from this because the median was 60, and if you remember, the mean was 57.5. So those are similar, but the mean of 57.5 has been pulled both down and up by the minimum and the maximum. So the 60 actually is dead center. So they are very close together. They're measures of central tendency, and you can actually do this quickly without even needing a calculator. Most of us can put numbers in order without needing a calculator to do it and then be able to count. And what I told you here actually tells you that your interquartile range is 71 minus 40, or 31. So there's only a distance of 31 between the 25th percentile and the 75th percentile. And what that interquartile range lets you do is it lets you figure out what the fences are. The interquartile range is always Q3 minus Q1. So in our case, it is 71 minus 40, which was 31. And its real purpose is to help us find whether we have any outliers. Now the calculator says that 120 is an outlier, but 6 is not. Let's see if we can verify that, because it looks to me like, 6 is pretty far away from everything else too. So I'm kind of wondering if that's absolutely the only outlier. So my lower fence is actually my first quartile minus 1.5 times the interquartile range. So my first quartile is 40 minus 1.5 times the interquartile range is 31.
Minus 6.5.
So indeed, the 6 is not an outlier because it's not less than negative 6.5. okay? But now the upper fence is Q3 plus 1.5 times your interquartile range. So that's 71 plus 1.5 times 31. Which is 117.5. So that's why the 120 is an outlier. It's actually above the upper fence. And if I can sort of visually help you with this, thinking about what those fences are and why are they what they are. This distance right here is actually the IQR. So if I measure that distance, I'm trying to be as accurate as I can, so I folded it in half, put another mark. This distance is plus another half IQR, so this whole distance is 1.5 interquartile range. That's that 30 or 31 plus another half a box, basically. Okay? So when I do that, I think I might be a little bit off because I think I folded that a little bit badly. But when I do that, what I'll see is that I'm adding, and my bottom fence is at negative 6.5, so it's going to be way down here. But my upper fence is at 117.5, which is pretty close to the 120. But the 120 is still just barely outside of it. So that's why 120 was an outlier.
Is there some like mathematical justification for this particular formula, 1.5 times IQ?
The 1.5 isn't magic. There is a mathematical formula for it. Basically, your interquartile range is what 50% of your data values are. Okay, it's the range of the middle 50%. So if you add half of that, you're basically saying, okay, 75% of your data, because half of 50% is 25%. So you're going from the upper fence, the width of the interquartile range, plus another 25%, so you're going up 75%. Now, if you think about that, you're going from 50% up to 125%. And if you have a data value that is outside of that 125% range, that would be very unusual. Okay?
But it seems like it's kind of arbitrarily 1.5. I mean, why not 1.4, 1.6? You know?
Well, there is a statistically justifiable reason for doing it. And we're going to look at this one right now, as a matter of fact. I didn't mention it earlier, but there's the range rule of thumb. Does anybody remember talking about the range rule of thumb? The range rule of thumb is in Chapter 3, and what the range rule of thumb says, and this is actually related to quality control. The range rule of thumb says that 95% of the data will be between the two numbers, the mean minus 2 standard deviations and the mean plus 2 standard deviations. So if I come back here where we calculated these two, the mean is 57.5. So the mean minus 2 standard deviations would be minus 25.24. And then the other side would be 57.5 plus 2 times 25.24. So a little quick arithmetic here. So according to the range rule of thumb, 95% of my data should have been between 7.02 and 107.98. Which still says that 6 is not an outlier, but 120 is. Okay? Now, the only issue with this is that it really only works well for sets of data that have a symmetrical bell-shaped distribution. It doesn't work nearly as well if you have a uniform distribution, if you have an asymmetrical distribution, or if you have a skewed distribution. It doesn't work really well because the mean gets pulled toward the extreme values, high or low, which pulls the center off. And then the standard deviation is going to be abnormally large if the extreme is abnormally outside the range of the rest of the data. So what this says is if 95% of the data is here, then only 5% of the time would you have values outside of that. And 5% in probabilities is a very low probability. You don't want to make any bets on something that only occurs 5% of the time. Okay? That's considered a very low probability, which means that any numbers outside of this range would be considered unusual, which is what an outlier is. Yes, ma'am?
So, when we were doing the lower fence, the number was negative 6.5. But 6 wasn't an outlier.
6 wasn't an outlier because 6 is within the range of negative 6 up to the median of the data. So 6 was inside the fence. 120 was outside the fence.
So why is, I guess it's...
The 6 is positive. The lower fence is actually 12 units below that. Over 12 units below that. 6, 5, 4, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6.2. Okay, so the lower fence is actually below 6.
What would it have to be to be an outlier?
Negative 7, negative 8, which, you know, in speeds of roller coasters wouldn't make any sense. Even 0 wouldn't be. Now, the reason we do this, like I said, this applies best to bell-shaped, relatively symmetrical, bell-shaped distributions, not things that have two modes, not things that are skewed right, skewed left, not things that are uniformly distributed. This works no matter how your data is distributed. Okay? It works no matter how your data is distributed. So if you have a data set that has a very large standard deviation, it still works. If it has a very small standard deviation, it still works. And it's an easy thing to do without having to do a lot of calculations, because as we very well remember when we learned how to calculate standard deviation, that's not an easy calculation. That's tough. We don't even want to do that by hand. Whereas doing this by hand really wasn't that big a deal. We were just rank ordering and counting. So remember, there's two ways to find outliers. One of them is the range rule of thumb if you have the mean and standard deviation. The other one is by finding the 5-number summary and getting the interquartile range, and then multiplying that interquartile range by 1.5. The 1.5 is just part of the formula, because basically if you look at the distance from the lower fence to the upper fence, you're looking at a range of from negative 25%, which I know doesn't make any sense, all the way up to 125%. And if something falls outside those two percentiles, it would be strange indeed. It would be very unusual. Which is probably why they really advertised that particular roller coaster, because 120 miles an hour at the time that roller coaster was built was really, really, really fast. Does anybody know if there's a roller coaster faster than 120 miles an hour? That might make a good bonus question on the test. Might want to Google that, see if you can find out.
That new one at Dollywood feels like it after...
Yeah, I have heard. I don't do roller coasters. It isn't healthy for the people below me. Okay. So let's back up so we can summarize. Back up to the previous 2 pages. Let's get rid of the calculator because we don't really need it right now. Percentiles are measures of position. They are not measures of center, they are not measures of spread. They are simply measures of position among a rank ordered set of data. If you've ever taken a standardized test, and all of you probably have, your measures of position are your percentiles. If you get, when they did the standardized test they do in public schools, they send a little report home that says, this student falls at the XX percentile of this test. Now, if that percentile was 90, then that meant that you were at the bottom of the upper 10%, or you were at the top of the lower 90%, whichever way you wanted to look at it. And I always thought it was neater to look at it that you were at the top of the lower 90%. If you're at the 50th percentile, you're dead center. Half the people that took the test scored worse than you, half of them scored better than you. It's just a measure of position, of relative standing, basically. So if you have the weight of an infant child was in the 78th percentile, that means the infant's weight is greater than 78% of all infants. It is not 78% of some ideal. Okay, so if you're at the 95th percentile, that doesn't mean you got a 95% on the test. That means you're higher scoring than 95% of the other people that took the test. And the reason we talk about that is because when we do box and whisker plots, we're talking about measures of position among the data set. The quartiles divide the data set into 4 equal groups regardless of the value. They just rank order the data and sort it out into 4 boxes, and there's 25% of your data in each box. So 25% of the data is in each group. Your 5-number summary is the minimum. Your first quartile, which we call Q1, separates the bottom 25% from the top 75%. Quartile 2, which we call Q2, and we also call the median, because that is what the median is. It's the 50th percentile. Separates the bottom 50% from the top 50%. And then quartile 3 is called Q3, and it separates the bottom 75% from the top 25%. And then you have the maximum. And your interquartile range is Q3 minus Q1. Okay? Let me see if we left out anything else, but I don't believe we did. We did coefficient of variation, right?
I don't think so.
We did not? Okay. Then let's look at example 6 so we can talk about coefficient of variation. What we have here is the heights and the weights of a selected sample of 8 players from the Atlanta Braves. Now we can find the mean of the heights, we can find the mean of the weights relatively easily. We can also find the standard deviation of both of them. And just for a quick review of how you do that one-bar stats, one more time. We'll go stat, edit, and I'm just going to delete all of these. I'm not going to clear them out. I'm just going to delete them all. I'm going to enter the heights in list 1. And then their weights in list 2. And we're going to calculate the mean and standard deviation for both. So first, we'll go stat, over to calc, 1-bar stats, second and the number 1 for list 1, and get that information. And since this is a sample, its X bar is 73.25. And S is 1.669. You could round the height off to 73.3 and the standard deviation to 1.67 if you wanted to. There's nothing miraculous or hard and fast about the way that I round it. If it's in my stat lab, round the way it tells you to. If it's on a test and I don't tell you, round however you want to. The only thing you don't ever do is you don't round the mean to a whole number, even if the data was whole numbers. You always have at least one more decimal place. And you also don't round the standard deviation to a whole number. Now we want to find the mean and standard deviation of the weights. So stat, calc, 1-bar stats, second 2 for list 2, and for the weights, the mean is 195.625. I'm just going to keep all the decimals. And the standard deviation is 21.454. tell me again, what does standard deviation actually measure? The average, the distance from the mean. Okay, it's measuring the average distance from the mean for all the data values collectively. It's based on the mean.
Over 68% of the area falls within one standard deviation on either side of the center of the normal distribution.
Right. That's true. That's the 68, 95, 99.7 rule. It's in Chapter 3. I don't emphasize it at this point, but it is in there. Okay. This standard deviation is only 1.669. This standard deviation is 21.45. Does that mean there's more variation in their weights than there is in their heights? Can we say that? The standard deviation is certainly larger, but the standard deviations are based upon the distance of the values from this number or this number. So we can't just generalize and say there's more variation in their weights than there is in their heights, although we'd like to, because it certainly looks like the standard deviation is larger. But remember, standard deviation is based upon distance from the mean, and this mean is obviously a lot larger than this mean.
Proportionality would be maybe the same.
They may be the same. They may be very similar in the variation. So you can't look just at the standard deviation to decide if you're comparing two groups that have means that are not similar. Then you can't look just at the standard deviation to decide which one has more variation. What you have to do is you calculate something called the coefficient of variation. And the coefficient of variation is the standard deviation. I'm going to write it up here and then I'll calculate it down here. It's the standard deviation over the mean or divided by the mean and then multiply by 100 to convert it into a percentage. Okay? So the coefficient of variation for the height is going to be that 1.669 divided by 73.25. And then I'm going to multiply it by 100, so I'm going to move the decimal 2 places. So the coefficient of variation for the heights is 2.28%, or we can call that 2.3%. That's going to work fine. And now we're going to do the same thing for their weights. We're going to take the mean, which is 195.625, and divide it into the standard deviation. We're going to multiply it by 100 and see what our coefficient of variation is. Now, before I actually multiply by 100, you look at this, you say, wow, that's going to be over 100%. No, it's not. That's 1.0966 times 10 to the negative 4. So this is actually decimal and then 3 zeros in front of that 1. So this is 0.01%.
This one,
Excuse me. Yes.
I don't think you put a decimal between
Did I? Oh, I did not, thank you. I see that now as soon as you said it. Thank you for catching that. That'll make a big difference on that answer too. Okay, so it's, we multiply by 100, it's times, it becomes 10.966%, or we'll call that, we can actually call that 11%. That's pretty close to 11%. That's 11% variation. So which one is more variable? There's greater variation in the weights than there was in the heights. Close to 5 times as much variation. Now think about why that might be true. Just thinking about the numbers. All of their heights are pretty much, let's see, that's 5'11", and the rest of them are over 6 feet tall. The tallest one is 6'4". Okay, so that's really not a lot of variation among those heights. But here, we're going from, let's see, the lightest one is 175, no, 170, and the heaviest one is 220. So their weights do vary more. And if you look at them based on their heights, this is a person that's 6 feet tall, weighs 185. This is a person that's 6 feet tall and weighs 175. And then here, this is a person that's 6'1" that weighs 175, and one that's 6'1" that weighs 170. So there are people that will have the same height but have more variation in their weight. Differences in body mass, differences in skeletal density. So it's going to contribute to more variability in their weight. Whereas their height's going to be basically just based on one thing, their skeleton, and that's it. Okay? So a coefficient of variation lets you compare two data sets for their variability if they don't have a similar mean. Now, if I was comparing grades for my two classes on the first exam, and one class made 74 and the other one made 76 for the average score, then I wouldn't really worry about it. I would look strictly at the standard deviation to decide which class had more variability. Because 72, 73, 74, things that are scores that are similar, you can compare them directly. But comparing means of 73 to 195, you don't want to compare those directly. And we did do, let me back up just a second. We did do this problem, right? The one about the NASA space flights? You don't have, okay, well, let's back up and do the NASA space flights so we can talk about the range rule of thumb and some of the other things that we've learned today. And I remember now that, let's back up. What does it require for a standard deviation to be 0? What do your data values have to look like?
And they all be the same.
They would have to all be the same. Okay? Because last time I did have you give me examples of a small standard deviation and a large standard deviation in a data set. So let's practice mean and standard deviation one more time again on the calculator. We're not going to do these by hand. I'm going to find the mean, standard deviation, and variance. So we're going to hit stat, enter, and I'll delete all of these just so that we don't have them taking up space. Keep it clean for the next person. And I'll delete all of those in list 1, and I'm going to enter in the space shuttle flight times. Okay, now, make sure your data is accurate. There's a saying in computer science, garbage in, garbage out. That means if you put garbage in, guess what you're going to get when you're done? Okay. Now, this data is a simple random sample, not a population, it's a simple random sample of all of the flights of NASA's space shuttle. We're going to find the mean, the standard deviation, and the variance. So we're going to hit stat, over to calc, 1 bar stats, second one for list 1. You always tell it which list you're using. And the mean is 217.3, repeating. And that'll be X bar because it is a sample. And the standard deviation is going to be 105.92. Which is actually pretty large. And the variance is the standard deviation squared. Now there's other ways to get it, but honestly the easiest way, since it's right there on the screen in front of you, type in 105.9202305 and then square it. And no, you do not round off before you square it. If you do, you'll introduce too much error. Because when you square numbers, even one small decimal left off changes the value significantly sometimes. So the variance, which is S squared, because literally you simply took the standard deviation and squared it, was 112.19 point, we'll call 0.95. Now, this number doesn't really tell us a whole lot of anything. It honestly doesn't. It doesn't tell us much of anything. This one, however, tells us that on the average, the individual space shuttle times varied from the mean of 217.3 by about 105.92 hours, because these are space flight times in hours. Okay? Does anybody see a value that looks suspicious in that data set?
0.
Yeah,
0. What does that 0 mean?
That was the Challenger.
That was the Space Shuttle Challenger.
I figured it was an explosion.
Yeah, it was an explosion. All because a bunch of NASA scientists could not do their probability and statistics correctly. There was an O-ring failure because they treated the O-rings as if they were independent probabilities, when in fact if one O-ring failed, they all failed. And that took the probability of O-ring failure from about 97 or 98% down to about, or it actually increased it quite a bit. So individually they were about 95, 96% foolproof, but when you consider that when one goes, they all go, that creates an unacceptable probability. Okay?
There was at least one guy who knew what he was talking about, and they didn't listen to him.
They didn't listen to him. So, is probability and statistics important? I think there were some families that thought so. So, we think that 0 time is a little unusual compared to the others, for whatever reason. Remember I mentioned to you the range rule of thumb. Right? The range rule of thumb for finding usual and unusual values is from the mean minus 2 standard deviations to the mean plus 2 standard deviations. Usually we're working with sample data values, so we usually write that very much more simply as x bar plus or minus 2s. That's your range rule of thumb. Anything that does not fall within this interval would only occur 5% of the time or less and is therefore considered to be unusual because 5% is a low probability, which we'll talk about in the next chapter. So using that example, is the lowest duration time unusual? Well, the mean was 217.3. And the standard deviation was 105.92. So we will calculate those two boundaries. So let's do the lower one first, so we'll minus. So from 5.46 to 429.14. So 0 would be unusual. There are no unusual upper values. The longest flight time on the table was 381 hours. So that's well within the upper boundary. Okay? And what's at the bottom of that page was the coefficient of variation. And remember, the measure of the coefficient of variation is the standard deviation divided by the mean times 100. You don't need to memorize that formula because I'm going to give you the formulas on the test. Okay? You don't need to memorize any formulas for anything. Anybody have questions about anything? Okay. We are pretty much done with Chapter 3 at this point. I'm going to go ahead and give you, I think I'm going to go ahead and give you all with me. I did not. I'll let y'all take a short break, about 10 minutes. And when we come back, I'll let you ask questions about anything that you're concerned about.